All right, welcome to 3.4 Basic Functions. We're going to look at all what we call the library of functions. What you're going to be able to need to do is see an equation and know what its graph is going to look like in its basic form. So we're going to start out with a constant function. This could be f of x is equal to some constant number, let's say 3. That's a horizontal line. It's a horizontal line for your graph. Then the next function is a linear function. Some authors call it the identity function. This would be y equals x, or f of x is equal to x. This would be a slanted line cutting quadrant 1 and quadrant 3 in half diagonally. And the reason it's called the identity function is because your x value is the same as your y value. They're identical, therefore identity function. Now you could have negative x, which would be a downhill slope, but anything constant, horizontal, any x to the first in the equation, and that's all you have for an x, is going to be some slanted line. Next, we have the square function, or a quadratic function. Now my x is raised to the power of 2. This will be some U-shaped curve opening upward. Now, does it have to be right here at the origin, at the relative min? No. It could be shifted up, it could be shifted down, to the left, to the right. Excuse me, and if the x squared had a negative being multiplied to the front, it would be opening down. Your cubic function, x cubed, f of x equals x cubed, or y equals x cubed. This is kind of like your quadratic, your U shape, but you took the left-hand side and you flipped it and twisted it over the x-axis, so you get this half of a U shape, or what we like to call parabola, going down and the other half going up. Now again, if I put a negative in front of that x cubed, it would flip it over the x-axis. It would come down, touch the origin, and keep going down. Next, we have the cube root of x function. It should be related in size and shape to the x cubed function. It's just that it's been turned to its side. And it's increasing because it's a positive. So as I read it from left to right, it's increasing. Notice it's increasing slower, if you will, than the x cubed. It's increasing really fast. After our cube root function, we have the absolute value function. Here you will see x inside of absolute value bars. So f of x equals the absolute value of x, or y equals the absolute value of x. Either way, it makes the shape of a V. It can be a wide V, it can be a skinny V, it could be shifted up, shifted down, left, right. The V could be opening down. This is just in its basic form. Our next function is a rational function. Now this rational function, or if you want to call it fractional function, because now your x is in the denominator. If you recall from earlier in this chapter, this meant we had a domain restriction. X is in the denominator of a fraction. X cannot equal 0, so therefore notice when x is 0, that's the y-axis. The red graph does not touch the y-axis. So when my x's are positive, 1 over a positive, I'll be in quadrant 1. But once you go past 1 for the x, here's 1, there's 1 over 1, y is 1. When your x keeps getting bigger and bigger and bigger, the overall value keeps getting smaller and smaller and smaller. And then as you go from 1 to 0, going to the left, now my x's are getting smaller, but 1 divided by a half, that would be 2. 1 divided by a third, that would be 3. 1 divided by a fourth, that would be a 4. So as your x's go from 1 and move to left to 0, now the graph's y's are getting bigger and bigger and bigger and going to run right along that y-axis. And if you put your x's in being negative, you should get the same style curve in quadrant 3. Stop and visualize. Put your pencil on the origin. Turn it 180 degrees. It looks exactly the same. This is symmetrical to the origin. If my x was a 2, I would be at 1/2 for my y, 2, comma, a half. Take the 2, make it negative. Negative 2, negative 1/2. For every positive x, there's a negative x, where your positive y goes to a negative y. Your y's change. Square root function. Y equals the square root of x, or y f of x equals the square root of x. Now here I put the 2 on the ledge, where that's our what we call our root or our index. A lot of times the author will not put that in. I like to put in the 2 to remind me that it's a 2. Just like if you're working with an exponent, and if there's no exponent there, you put a 1. This is a half of a parabola opening to the right. But again, it could open to the right, it could open to the left. It could open to the right and go down. It could flip it over the x-axis. It could go to the left and down. This can go in many different directions. Our next crazy function is called the greatest integer function. It has 2 notations. Our calculator notation is int of x. And symbol-wise, it looks like a double pair of brackets that are next to each other. Don't say absolute value bars, because nothing in here is going to generate positives all the time. Now, a lot of people think that, oh, you just drop the negative. So if x happened to be 1.5, you drop off the 0.5 and you're at 1. That's not the case. The way you find your y coordinates is, again, you read the graph from left to right. This is why it's called the greatest integer. So -1, -2, -3, here's -4. Whoops, go back. Here's -4. As I read it from left to right, as soon as I hit -4, that was the last integer I hit. So when I'm at -3.5, I don't drop the 0.5 and call it -3. The last integer that you touched, going from left to right, was -4. So I stay at -4 till for my y's until my next biggest integer is now -3. So my y's jump up to -3. And they stay at -3 until my x's hit the next biggest integer, -2. They stay there till I hit -1. Same thing. When I hit 0, it stays at 0 till I hit 1. So it kind of gives you this floating staircase look. Left endpoints are always solid. Right endpoints on these little horizontal segments are always an open circle. That's our greatest integer function. So again, noticing the function, the symbols that you're given, you need to recognize, oh, that's what the graph is going to look like. Make sure you know the family or library of functions. You will have that on the test. You need to know every one of them. All right. Next, we have what is known as continuous functions and discontinuous functions. A continuous function is a function where the graph has no gaps, holes, or breaks. A quick and easy working definition is simply this. It can be drawn without stopping and lifting your pencil. You can stop, just don't lift your pencil. So if I can trace it without stopping and picking up my pencil and starting somewhere else, it's continuous. Discontinuous means I can't draw it. I will have to stop, I'll have to pick up my pencil, put it somewhere else, and start up again. So if we go backwards to my functions here, back to the beginning, I can trace it, continuous. continuous, 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 continuous. Oh, continuous. I can trace it. I am going to stop, but I didn't pick up my pencil. I just redirected from there. And there's the rest of my graph. Whoops. Discontinuous. I trace it. I got to stop, pick up my pencil, jump up to here, and restart. Discontinuous. This is continuous. Start at the close point and move forever. Oh, all discontinuous. Horizontal segment, pick it up, jump. Draw a segment, pick it up, jump. All kinds of gaps here. This is discontinuous. All right. So that's the difference between a continuous function and a discontinuous function.